All right, let's take a look at topic number 10, more about functions. So I have three of these, one, two, and three. Okay. So in this one, in this topic, I'm gonna first take a look at determine the domain of a function defined by an equation. Okay, defined by an equation. So remember, y is a function of x. This is very important. Instead of saying y equal, all the y equal is going to turn into f of x. Okay, they are the same thing. So to determine the domain of a square root function, so if I give you a square root function right here, okay, to find out what the domain is without graphing, because now graphing still may not be able to tell you, about the domain. What you're gonna do is set what's inside the square root function, or set what's inside the square root, or we call them radicand, remember, equal to 0 and solve for x. To determine the domain of a rational function, we're going to set the denominator not equal to x and solve for x. So the restriction on the variable, the wording I used before, is really called the restriction on the domain. Okay, you got to find the restriction on the domain for rational function. What x cannot be. You need to predetermine that arithmetically. So when you look at the graph is not going to tell you what x cannot be. Remember, our graph, our table is set up where it's only do integers. So if my restriction turns out to be a fraction, then the table is not going to tell me that. Okay, so that's the reason why we still need to know how to find those restrictions. Okay, ahead of time. So when we graph it, we know what we are looking at. All right. Earlier. So let's check this out. For the following function, determine the domain. So I just want to do domain and express the answer as an interval notation. Okay. What kind of function is this one? You got to first determine. So the answer to that question is, okay, look at this function and think back on all the graph we drew. From topic number 9, the graph we drew. Okay. I wrote the form. Does that equation, does that function look like a linear function? Does that look like a quadratic function? Does that look like a rational function? Does it look like absolute value? Does it look like a cubic function? So by looking at this example, oops, not number 4, number 10. By looking at this function, which one is these pictures? Well, I don't see any square root or cube root, so I know those two are out, right? I know I don't see an absolute value symbol, so that's out. I don't see any fractions, so those are out. All right, so is it linear? Is it a quadratic or is it a cubic function? Well, it's not linear because I have an exponent higher than 1. It's not a quadratic because quadratic function, the highest exponent is 2. So this highest exponent is 3. So this must be the cubic function. And I know cubic function already, normally the basic one looks something like, oops, sorry. The basic one looks something like this, right? So if I will graph it, -4 plus 2x minus x to the third. It looks something like this way. So by looking at this picture, what is the domain? It don't quite look like the basic one, and there's a reason for that. This basic one was actually f of x equal to x to the third, and this is a positive x to the third. This cubic function is a negative x to the third. So the graph flipped, and we'll talk more about that too. There's a reason for it. But what's the domain? Well, look on this side. This keep on going left and up. This side keep on going right and down. So the domain, if you draw the graph from left to the right, coming from negative infinity, right, coming from very left and keep on going to the very right. So domain will still be negative infinity to infinity. So like I said in topic 9, cubic function domain is already set. It's always going to be negative infinity to positive infinity for cubic functions. Okay. Square root function, it depends. Square root function, rational function, domain can change. And they change based on what's inside the square root or the cube, what's inside the square root or inside the even root, excuse me. So for even root functions or square root functions, we can set what's inside the square root or the even root equal to 0 and solve for x. Okay. And a lot of students say, well, Mr. Chen, I can just graph it and I can tell, what the domain is. I do agree to a certain extent, because if I will dress this thing up with a negative 2x plus 3, then you will not be able to tell. Okay. So that's why the easiest way to do it is set what's inside the square root equal to 0 and solve for x. That's how we predetermined. Let me move this over here. Let me do on the side here. Sorry. All right, since my variable is negative, I'm gonna move the negative x over, but because that instantly become positive 3. All right, so my x is 3, right? But I'm still not quite sure what my domain is until I graph it. So here, I'm gonna give a try. So what does that positive 3 mean? Well, we'll have to see. Square root, I don't even know. Negative x plus 3, right? See right now the square root automatically opens a parenthesis. That parenthesis means whatever I type inside the parenthesis goes in underneath the square root. So before I enter -2, I'm gonna close that parenthesis. So make sure if your syntax look a little bit different than mine, if your syntax look like what I printed here, then move the cursor outside your square root before you say -2. All right, and graph. Well, we thought square root function normally look something like this. Well, not this one. This one actually went the other way. This one went the other way. So the x equal to 3 we just solved. Take a wild guess what that 3 means. That 3, that x equal to 3 is not where the domain begins. Since my square root function is going to the left or coming from the left, but it actually ends right here when x is equal to 3. That's what that 3 is. That's where my domain actually ends at. So even though the graph is going the other way, if you set what's inside the square root equal to 0, it will tell you whether that point is where it begins or where it ends at. So my domain, looking at this graph from left to the right, is coming from very left, right, all the way to the x value equal to 3. And that point 3 is on the line, so you got to be a bracket because nothing existed to the right side of 3. Because if I would put positive 4 right here for x, then what's inside the square root will all become a negative answer. So if I go to my table, you will see after 3, every single x value you put in, the y value will be an error because they all going to become imaginary numbers. So that will be the domain. All right, rational function here. I'm going to predetermine what my x cannot be. So I'm gonna set I'm gonna set my denominator not equal to 0 and solve for x. Move the -1 over, I should get 2x not equal to +1, divide both sides by 2. X is not equal to a half. So my restriction on the domain is gonna be x cannot be a half. So I got 2 term on the numerator, I got 2 term in the denominator. So I got to start up with the parentheses. I got to make sure the calculator see this as 1 term over 1 term by put the x minus 4 in the parentheses. There's 2 terms representing 1 numerator. Put in the parentheses, divided by 2x minus 1, and put them in the separate parentheses. Got to be 1 term over 1 term. And this is what this rational function looks like. Similar to the one we saw earlier, where the denominator is to the first power, right? It's an I power down here. But I know ahead of time, x cannot be a half. I know x cannot be a half, but I'm not going to be able to see it on my table because my table is only using integers. Okay. But I know this part keep on going to the left. Okay, coming from left, right? Approaching to half, but it cannot be half. My y value is going nuts. God knows where that thing goes. And on the other side of the half, my function appear again and keep on going to the right. So in terms of domain, coming from the left will be negative infinity all the way to half. I cannot be half, that's why I use a parenthesis. Or my graph existed from the other side of half, right? Again, using parenthesis and keep on going to the right to positive infinity. Okay. Now this question on the right, this question right here on the right is a very unique problem. But I'm gonna approach it the same way. I'm gonna set the denominator not equal to 0 and solve for x. And what do you see right here? That's a difference of squares, right? That's a difference of squares. So I can actually factor my difference of square. And that should give me x plus 3, x minus 3. Set each factor not equal to 0. All right, move my positive 3 and negative 3 to the other side. My x cannot be negative 3. The other x cannot be positive 3. I'm gonna graph it. So I got 2 restrictions on the domain. All right, parenthesis x minus 3, close parenthesis, divided by. I'm gonna put these 2 terms in a separate parenthesis, x squared minus 9. Okay, that's all it shows. All right. So what's happening right here? What's happening right there is this line is keep on going to the right and it's hovering right above the x-axis, but it's so close to it. Cause so remember on the x-axis, y values are 0, right? On the x-axis, y values are 0, but so right above it, slightly above the x-axis, those y values are 0 point something. So if you hover right above it, that means those y values are 0.00 something. So if you look on the table, as the x value keep on going to the right or keep on getting larger, see it's 0.09, 0.08, 0.07. So that means that means the line is barely just above it. That's why it doesn't really show you all the way to the right, because it's so close to it, you can't even tell it's there. Okay. The only way you can see it is actually squeeze this y-axis all the way to like -1 to 1. Then you might be able to see it. But for right now, what I need is the domain. So remember, the graph didn't stop going to the right, even though the graph is not showing it. But on the table, on the table, my x value can keep on going larger, or my x value can keep on going smaller or going to the left. So I'm gonna barely kind of draw is, oh, just hover right above it. Okay, hover right above it. Keep on going, hover right above it. So the domain is from -infinity all the way to -3. Right, -3 got to be the first value that I will reach, but I cannot get there. I cannot be -3. All right, and then union, my graph will pick up on the other side of x equal to -3. Keep on going to the right, right? But here's the thing, I had two restrictions. Okay, I got two restrictions. X cannot equal to 3 as well. So my domain, my x values are from -3 to 3, but cannot be 3. That's why I use another parenthesis. But then if I will keep on hovering, right? That means the graph will pick up on the other side of +3 and keep on going to infinity. So what's happening here is, see right here, this is actually, this darker part of the graph is probably already past 3 already. But if you look closely on the table, when x equal to 3, there's an error message here. It's different than at -3. At -3, you can see the graph kind of broken apart, right? One of them is right here on the left side of -3. The other piece is on the right side of -3. But at 3, it also says another error, because what you don't see is when x equal to 3, there's actually a hole right here. That's actually a hole. And where does that hole come from? I will let you know in a different topic. Okay, we'll talk more about, we will have a topic just on rational function alone. But for right now, I just want you to kind of know, okay, there's a hole there, but I don't know, I don't see the hole. But I really want you to focus more on the domain part. Okay, then keep on going to the right. So you use the restriction that you found arithmetically to help you to understanding what you're looking at. All right, determine the domain and the range of a function defined by the graph. So these are based on graph. All right, these are based on graph. Let me make this a little bit bigger. All right, I drew this one right here. Okay, this problem tricks student up all the time. Domain and range. Okay, so what I always like to do is show you the arrows. This arrow is pointing left, right? I'm keep on going leftward, right? If I just follow the line, but I'm also keep on going down at the same time. All right, so go from left to right, coming from very, very left and down, right, to this point, and then I'm going horizontal. So I know this part is keep on going to the right. So as far as left to the right, the width of this graph, my domain got to be from what? Got to be from -infinity to infinity. Okay, what about range? What about its y values on this graph? Well, keep on going down means my range got to be from small to large, got to be from -infinity, right? Coming down from -infinity for the y values, all the way up to up this point right here. And then I begin to go horizontal. So range is about y value. So at this point, I know the graph is kind of hard to see. At this point, what do you think the y value is? Range is about y values. What do you think the y value is at that point? And then keep on going. Remember, horizontal line, all the y values are the same. So if you knew what this y value is, so is rest of the y value. What do you think this y value is?
1.
Nope, close. I'm still below the x-axis.
-1, sorry.
Yep, -1. Right? At this point, this is the highest y value you ever reached. So that y value is -1, and then everything is going right. So all these y values are still -1. And -1 is on the line, so I use a bracket. Yeah, that was tricky. I know it's kind of small, but that is at highest y value is at -1. All right, circle graph. Circle graph is not a function. Circle graph is not a function, but I can still write a domain for it. Okay, so if this is the origin right here, left to the right, the trick here is write down your coordinate. I'm looking at left to right, so I'm only going to write down my x value. What is the x value here? -1, -2, -3, right? X value here, +1, +2, +3. So my domain, the width of this circle graph is only from -3 to +3. Using brackets because both of these points are on the line. Range, down and up. Range is about its y value. So I'm only going to write down the coordinates for the y value. So this must be what? 1, 2, 3, -3. That must be +3 for the y value. So my range is also from -3 to +3 using brackets. Okay. Now this one here on the right, see this point right here? This is where everything ends. Okay. So the other side is keep on going left and up. All right. So in terms of domain, coming from left and it stops right here. Domain, what's the x value here? 1, right? So my domain from left to the right must be from -infinity all the way to 1. And that one is on the line, so I use a bracket. The range is where students are messed up on. Students say, okay, if this is where the function ends at, then my range will be from 1, keep on going up. And that will be incorrect. Because the y value 1 right here, this y value is 1, right? 1, 1. This y value 1 is not the lowest point of this graph. The lowest point in terms of down and up, the lowest point is right here. And the y value there is 0. So your range is actually from 0, keep on going up to infinity. Okay, a little bit trickier. All right, that's it right here. The difference between an open circle and a solid circle means included or not included. So that tiny little thing right there, what the domain left to the right must be from 1 to 2, right? X value, X value, X value, left to right, left to right. X value is 1, X value is 2. All right, open circle means I gotta use parenthesis for that 1. Solid circle means I use a bracket for that 2. The range. What is the range? What do you think the range is? Very tricky, but it's a very easy answer.
3.
Okay. People, I have seen this before. Does this make sense? 3 to 3. So it's just 3, right? So you remember interval notation is describing a range of answers. My answer is simply just 3. So if I only have one answer, 3, then I cannot use interval notation. I will use set notation by put my 3 inside the brace. That's how we actually describe it. Because this tells the reader that your range is only just one number. Without looking at the graph, the reader can tell that's just a 3. All your y value is just 3. Okay. So if your y value or your x value, if your range or domain is only one number, then you put them in the brace, in the set notation. All right, this one, open circle starting out with, okay? This thing's domain left to right wise, you got to start at that point. So the x value is 2, right? Open circle means I'm not including 2, so I use parenthesis. Keep on going to the right. The range will be the same thing, the y value for the range, okay? Starting at 2 and keep on going up to infinity. All right. In the previous topic, we said the domain for parabola is always set. It's always going to be from keep on going left and keep on going right, negative infinity to positive infinity, from left to the right. Range, tricky, right here. This is the lowest point. So the y value there, since that lowest point is on the x-axis, I know on the x-axis, all the y values are 0. So my range got to be from 0, keep on going up. So asking you this question one more time. Where are y equal to 0 at on the graph? What would you say? See if you remember. Where are all the y value equal to 0 at on the graph?
On the y-axis.
No, on the
X.
x-axis. The y-axis is opposite. The y-axis up and down. The x are 0. Yeah, that is important. Because we'll spend a lot of time talking about that y equal to 0 later on. All right. Determine whether the relation representing a function. Okay, so if you look at this example here, these are just equations. Okay, I'm gonna give you some equations, and what I'm asking you is, are these equations, or a different wording will be, are these relations, okay, represent y as a function of x? What they're asking you is, can you write this relation as in terms of y equal to f of x? So in order to write them as y equal, in order to think of them as y equal to f of x, you got to actually have a y equal first. So that's the reason why, to determine whether the relation representing y as a function of x, you got to solve for y. Because if you can turn these into y equal, if you can turn them into y equal, then y is the same as f of x, then we can actually say they are a function. Okay, remember, y equal to f of x means y is the f of x. F of x is equal to y. So if I can get y by itself, then that y equal can be replaced with the function of x. Okay, so all we want to do here is simply solve for y. See if we can do it. All right, solve for y. So now my variable term got to be the term involving with y. So this got to be my variable term. It's negative, so I'm going to move it over to the other side. So right away, I should get positive 7y to the third equal to x. All right, so to get y to the third by itself, I will need to divide both sides by 7. So I get y to the, this is not square root now, this is to the third power, okay? This is x over 7. So to get y by itself, similar to solving x squared equations, since I only got 2 terms, I can just simply take a cube root on both sides. Remember how we take a square root on both sides before? Here we can take a cube root on both sides. So we get y is equal to cube root of x over 7 or 1 over 7x either way. Okay. So we just wrote that relation as y equal. If we did, then this is a function. If it is a function, then you can graph it in the calculator. See, I'm gonna go to math. I'm gonna do number 4. This is a cube root function. And inside that parenthesis, I'm gonna do x over 7, close parentheses, right? And graph it. It looked just like the regular cube root of x. It looked just like the one was drawn in topic number 7. But allow me to write this slightly different so you can see it. Okay. You agree I can write x, I can write this as x 1 over 7x, right? I can write this as cube root of 1 over 7x. So you see, without looking at that 1 over 7, this is a cubic function. So the dress up part, the make up part is the 1 over 7 in front of it. Now 1 over 7 make my original cubic function look slightly different. It alters it slightly. Now it look like that. And we'll talk about how it alters in a different topic. All right, so it is a function. It is a cubic function. All right, I'm gonna skip that one. I'm gonna go to this one right below it. I need to solve for y. Right now, my variable term is trapped inside the square root. So guess what I'm gonna do? I'm gonna, since there's only 2 terms, I'm gonna square square both sides. I'm gonna square both sides because square and square root cancels out. So I get 3 minus y squared equal to x squared. So since I'm solving for y, my variable term is negative. So I'm gonna move this over and bring the x squared back. But this time when I bring the x squared back, I'm gonna put right in front of the positive 3, okay? So this is y squared equal to negative x squared plus 3. So to get y by itself, I would need to take a square root on both sides. One, okay, both sides, not every term. So that means these 2 terms on the right side will all be underneath the same square roots. Whenever we take a square root on both sides, the answer got to be positive, negative. Okay, that was the rule for the square root property. So now I get y is equal to positive and negative square root of negative x squared plus 3. So this thing looks like a square root function, but it is not. And the reason why it is not, number one, you actually have 2 answers here. Y is equal to a positive square root of negative x squared plus 3. Y is also equal to the negative 1. So you actually need to put both of them in the calculator. If you put both of them in the calculator, you have to view this graph as a single graph. So y is equal to positive square root of negative x squared plus 3. I'm gonna go down to y2 and type in negative square root of negative x squared plus 3. Oh, for negative sign, you gotta use this symbol, right? You gotta use this represent the decimal, okay? You cannot use negative as a subtraction sign. All right, I need to graph both of them and view this picture as one picture. That is not a function. All right. And the reason why it's not a function is because this thing called the vertical line test. Remember, to be a function, you cannot have the same x value. And guess what? Vertical line has the equation says x equal to number. It means all the x values are the same. So because vertical line has all the x values that are the same, we're going to use this line to see if our pictures, graphs are a function, not a function. Because if this vertical line touches my graph twice, if it touches my graph twice, that means I have the same x value. Think about it. Don't you agree? This x value right here is the same as that x value. All right. So if the vertical line touch a graph more than one time, it's not a function. That's the reason why this is not a function, because you have to look at this two equation we keyed in as one graph. See right here? Not a function. Touch it twice. Okay. So this relation is not a function. All right. This one right here, very similar to the one we just did. Solving for y. This is a variable term. I'm going to move the x squared over. So I get y squared equal to negative x squared plus 1. So it looked just like what I did right here. Y squared equal to negative x squared. Take a square root on both sides. My answer would simply be y equals positive and negative square root of negative x squared plus 1. So if I graph this again like I just did with that previous problem, it will still show the same, it will still show a similar circle graph. So it is not a function. All right, this one here. I think a problem like this will be on the homework, on the handwritten portion. The way to solve for y, since the y is trapped between two different variable terms, we're gonna use cross product. The x look at the x as x over 1. I'm gonna use cross product. I'm gonna say x will times those two terms, 1 will times those two terms. So x will multiply 5y minus 1. I'm gonna go ahead and put them in the parenthesis for right now. Set it equal to 1 times those two terms is 7y plus 3. Distribute my x to bring the 5y out. I get 5xy minus x equals 7y plus 3. So now, remember I'm solving for y, so the terms with the y are my variable term. Got one here, one here. Okay, and these two are not like terms. They're all variable terms, but they are not like terms. I cannot combine them, but I still need to have them on the same side of the equal sign. So I'm gonna move the 7y to the left side. Move the negative x to the right. So my 5xy positive still. Positive 7y come over, become negative, equals negative x come over, become positive. So you can say 3 plus x or x plus 3, either way. So what do I do from here? If these two terms are not like terms, I cannot combine them. So how can I make these two letters of y into one single y? I gotta solve for y. I gotta get y equal. Right now I got y in two different terms. So this is where the factoring comes in. You see, the greatest common factor between these two terms is actually the letter y, because it repeats. So what I can do is factor out my greatest common factor y. So that's how I make two letters of y into one of them, by factor it out. All right, so what's left between the two terms are 5x minus 7. And to get y by itself, I simply just divide both sides by 5x minus 7. So you see, as long as I'm able to get y by itself, and it's not crazy problem like a positive and negative answer, these should be functions. These are functions. Okay, this is just simply a rational function. All right, so vertical line test, kind of mentioned it already. Make sure vertical line test does not touch the graph more than one time. So if I draw a vertical line on this linear function, I know this is a linear function, so it's a function. All right, this is an ellipse. Vertical line will touch it twice, so it's not a function. Not a function. Horizontal line, of course, is a function. Parabola open down is a function. You only touch it one time. But parabola open to the right or left are not a function. These are not functions. So what are they? We can just call them the word relation. Okay. This relation is not a function. Not a function means y does not defined as a f of x. You cannot use y as equal to f of x. Y does not define the function as x. All right. How do you determine domain of a square root function? We set what's inside the square root. I think right here, beginning, it says set inside the square root. Set what's inside the square root equal to 0 and solve for x. That's all you had to put. How do you determine the domain of a rational function? Set a denominator not equal to 0 and solve for x. Okay, so those are coming from the handout straight up. To determine whether the relation y as a function of x, okay, what we just did is solving for y. So to determine whether the relation represents y as a function of x, I think the definition here says solve for the variable y. Okay, that's all you have to put. Question number 4. All right, consider the following function, determine the domain. So if you want to, go ahead and solve for x in the denominator so you know what the restriction is, and then you can actually type it out, okay, using the interval notation. Make sure you use the interval notation, okay, using the graphic equation. And graph it if you need to graph it to help you see the graph a little bit better. I just show you how to solve this one. Solve for y. So all I need you to do is tell me what y is equal to. So the way you do it on paper is you set them as x over 1 and you use a cross product, okay? And do the same step as I did to solve for y. Okay, it's just, I just changed the numbers. It's still, all the steps are still the same. Once you solve for y equal, okay, enter, solve for y. So what you're gonna enter using graphic equation is y equal to whatever, right? Once you solve, once you enter this answer, from the answer in number 1, find the restriction on the domain. Okay, so that means set, once you write out this answer, set your denominator not equal to 0 and solve for x. And that's what you're gonna enter for number 2. Just make sure you say x not equal to whatever you write down the range. Just the range. I don't need domain. All right, consider the following function, determine a graph. Relation are function or not. So for this one, all you gotta do is the vertical line test. So yes, it is a function. All right. So sorry, I went over a little bit too long today. That will be all for topic number 10. Hey, is everybody still with me?